Hey everyone, welcome to this explainer. We're going to create a little quiet space today to explore the actually really beautiful science behind the energy that effortlessly powers our modern world. Whether you're studying late in your dorm room, walking across campus with your headphones on, or just taking a moment to relax, you are constantly surrounded by invisible power. Now don't worry, today we aren't going to look at overwhelming equations or stressful textbook diagrams. Instead, we're just going to calmly explore how chemistry quietly supports your entire day. We'll look at the power in your pocket, the heavy lifters of the grid, and the next generation of clean energy. Okay, let's dive right in.
Take a second and just look at the device in your hands, or the laptop sitting on your desk. What invisible chemical forces are keeping that screen glowing right at this very second? It's so easy to take for granted, right? But inside that sleek metal and glass is a tiny, perfectly orchestrated environment literally working tirelessly for you. It all comes down to what chemists call a galvanic cell. Basically, this is a tiny, totally silent environment where chemical changes are peacefully converted directly into the electrical energy you're using. There's no noise, no moving gears, no exhaust, just a graceful exchange of electrons happening on a microscopic level, turning stored chemical potential into the spark that connects you to the world.
For portable devices like your phone, this is usually a lithium-ion cell. And what's really wild is how it works. It brilliantly relies on this gentle transport of lithium ions moving back and forth through an electrolyte. It doesn't use highly reactive, dangerous metallic lithium. Instead, it relies on this smooth, reversible flow. When you charge it up, you push the ions one way. When you scroll on your phone, they naturally flow back, releasing energy. It's kind of like a microscopic tide flowing in and out.
Section 1. Portable power, the energy in your pocket.
So when we think about portable power, there are really two main ways we carry energy around with us. First, we have primary batteries. Think of a standard alkaline AA battery. It can only discharge. It's basically like a disposable paper cup. Once you drink what's inside, or in this case use up the chemical reactants, it's done. But then we have secondary batteries, like the lithium ion we just talked about. These are your favorite reusable travel mug. By plugging your charger into the wall, you reverse the chemical reaction and fill that mug back up, over and over again. For any rechargeable battery to actually be useful to us, without causing us daily stress, it needs to hit 3 sweet spots. First, high energy density. It has to pack a massive amount of energy into a super light, compact space, because literally no one wants to carry around a brick in their backpack. Second, it needs a long cycle life, meaning it survives hundreds of recharges before dying. And third, stable chemistry with solid safety features, so it doesn't overheat. When a battery hits these 3 marks, it just fades into the background and quietly does its job.
Section 2. The heavy lifters, traditional chemical fuels. Okay, while batteries perfectly power our personal bubbles, we have to zoom out for a second. Batteries don't create energy out of nowhere, right? They just store it. We have to look at the heavy lifters, traditional chemical fuels that actually charge the broader electrical grid your wall outlet relies on. To understand fossil fuels without the academic overwhelm, you just need one elegant concept: calorific value. This simply tells us how much heat is patiently waiting inside a specific material to be released when it burns. A high calorific value means a tiny amount of fuel can release a tremendous amount of energy. Looking at the whole family tree of chemical fuels, whether it's ancient solid coal, liquid petroleum drawn from deep inside the Earth's crust, or natural gas, they are all essentially the exact same thing at a fundamental level. They're just densely packed, stored energy, mostly carbon and hydrogen, just waiting for a reaction to wake them up. And from these primary natural sources, we derive secondary, artificial fuels, like the petrol for your car or the coke used in manufacturing. And how do we wake those fuels up? Through combustion. It's a massive, fiery, exothermic chemical reaction happening far away from us in power plants. It violently breaks the chemical bonds of that ancient carbon and hydrogen, releasing massive amounts of heat. That heat boils water, creates steam, spins a turbine, and generates the seamless electricity that eventually travels miles down a wire right to the outlet in your room. Section 3. The next generation. Bridging the gap with fuel cells. So we have quiet, clean batteries that run out of juice, and we have continuous but dirty combustion fuels. What if we could combine the quiet, clean nature of a battery with the sheer, continuous power of traditional fuels? That brings us to fuel cells, specifically continuous flow systems like the methanol-oxygen fuel cell. It is such an elegant piece of technology. A fuel cell generates electricity directly through continuous chemical redox reactions, just like a battery, but without actually burning the fuel at all.
Methanol vapor enters on one side, oxygen on the other, and electrons are forced through an external circuit to power a device, all while producing incredibly benign byproducts like water. The really crucial difference here is how these technologies hold energy. Unlike a battery that holds a highly limited, closed amount of stored reactants and eventually, well, dies on you in the middle of a lecture, a fuel cell is like a river. As long as you gently and continuously flow fuel and oxygen into it from an external tank, it will continuously give you power. It never needs to be plugged in to recharge, it just needs a steady stream of fuel. You're probably wondering, so why aren't we using them for absolutely everything right now? Well, the reality of fuel cells is a mix of high promise and some pretty tough current limitations. They offer a beautiful, high-efficiency conversion of up to 75%, which is way higher than traditional combustion engines, and they produce environmentally acceptable byproducts. But they currently require incredibly expensive noble metals like platinum and silver to act as catalysts. Plus, safely storing large, lightweight volumes of hydrogen gas is extremely difficult. So they're a technology we are still patiently nurturing for the future.
Section 4. A peaceful power takeaway. Mindfulness in energy consumption.
Let's bring this all back down to earth. What does this science mean for you today, right now, outside the classroom? Honestly, simply having a proper knowledge of these invisible forces completely shifts your perspective. Understanding how much chemical effort, from the quiet dance of lithium ions to the roar of a distant power plant, goes into creating a single spark can help us become much more grounded, appreciative consumers of the energy we use every single day. Every time you plug your phone in, you are literally connecting to a vast, complex web of chemical ingenuity.
So as you wrap up this explainer and step back into your day, I want you to take a quiet moment. Notice the hum of your mini fridge, the warmth of your laptop battery, the light from your desk lamp. They aren't just utilities, they're the result of an incredible human understanding of the natural world. How will you mindfully use your energy, and the energy quietly working for you, today? Thank you so much for exploring with me, and I hope this leaves you with a little more peace and a lot more curiosity.